Introduction to fluid flow in a 90-degree bend pipe. The precise impact of fittings on pipe system is typically poorly considered when designing piping system. For single-phase flow, their impact on the overall pressure drop can be considerable. The determination of pressure drop in bands with single-phase flow is the main emphasis of this work. In a forthcoming work, an extension to multi-phase flow will be discussed. Single-phase deflected flow can be arbitrarily separated into two different scenarios. One for abrupt elbow bends at high RD values and the other for curved pipe and at high RD values. Although they are clearly related, the former often has fully developed flow with almost no inlet or outlet tangent effects, while the latter elbow bend has undeveloped flow with both inlet and outlet tangent effects. Theory to fluid flow in a 90-degree bend pipe. The measurement and forecasting of pressure drop in curved pipes and elbow bends for laminar and turbulent single-phase fluid flow are examined. Both theoretical and empirical relationship can be used to predict the pressure loss for curved pipe in laminar flow. An empirical relationship can be used to predict the transitional Reynolds numbers. Turbulent flow in curved pipes can only be theoretically predicted for large bands, but there are a large number of empirical relations that have proved to be accurate. Elbow bends have proven to be difficult to both measure and represent the pressure loss. Methods of overcoming such problems are outlined. There was no reliable method for theoretically predicting pressure drop in elbow bends. Experimental measurements show considerable scatter unless care was taken to eliminate extraneous effects. Reliable data are highlighted. An empirical method is proposed for calculation of pressure drop in elbow bends. For the adjective, application of new plane creation using point and normal options, inflation layer setup in meshing, solver setup for turbulent flow modeling, and the last one is output parameter setup. Thank you.
When we want to start our work, first we need to run the workbench as administrator. After the workbench is open, then double click on the fluid fluent. After that, right click geometry and press new design modeler. Select the YZ plane, click sketch, then press line. Draw line at Y and Z axis and then make a fillet at the angle. Press modify, then choose fillet. After that, we need to enter the dimension on each line and the fillet. Click dimension, then choose general. After that, click on the line that you wanted and enter the specified length. Repeat the same step for fillet radius. Then rename the bending section. After that, create new plane. Choose create new plane and then choose from point and normal. Select the point at the end of the H1 line as the base point. And for defining the normal, choose the H1 line. After creating the plane, click the YZ plane and then right click on sketch 1 and then choose always show. Go to plane 4 and sketch circle at the end of line H1. Enter a diameter of 10 mm. Select sweep and choose the circle as the profile and the H1 line as the path and then generate. After we done creating our geometry, we will do the meshing for the geometry. Right click on mesh and press edit. We will first generate the default mesh by right click on mesh and then choose generate mesh. After that, right click on mesh once again, go to insert and choose sizing. Choose the area at the bend and change the element size to 0.5 mm and set the behavior to hard. And then once again, right click on mesh and go to insert and choose inflation. Select the whole body as the boundary and then set max layer to 4. After we done, once again right click on mesh and then choose generate mesh. When we done generating the mesh, change display style to skewness and max aspect ratio for analysis the mesh. Right click on the mesh once again and then choose update. After that, click file and choose close meshing.
After we have done meshing, now we open Workbench and right click on solution. Set up all the velocity and the k epsilon, and now we are done. We can start the calculation. After we have done the calculation, and now we can get the result.
After every step is done, we now have got the result. We can check the result by clicking on the result menu. This is the result for velocity at the outlet. This is the result for velocity at the inlet. This is the result for pressure acting on the whole geometry. This is the result for velocity acting on the whole geometry. This is the skewness and aspect ratio for the meshing. In conclusion, meshing at the area of bending is more compact and dense compared to the outlet and inlet wall. The highest pressure is located at the inlet and the lowest pressure is located at the outlet. After done calculating, we get that the final velocity is 5.2247 meter per second.